when the legendary tunnel boring machine, known as Bertha, was officially retired. Most people believed the story had ended there, but beneath the streets of the United States, something far bigger was already taking shape. Without press conferences, without headlines, and far from international attention, a new and colossal machine began carving its way underground. Residents noticed strange tremors beneath their feet. Thick clouds of dust appeared without warning. Nights were filled with deep mechanical echoes that seemed to come from nowhere. For years, no one could explain what was really happening. Only after a long investigation did the truth finally emerge. The United States had secretly commissioned an even more massive tunnel boring machine, one designed to redefine underground transportation forever. So just how enormous is this hidden giant? But before we begin, don't forget to like the video and subscribe to our channel. To accelerate national progress in construction and structural development, the United States commissioned a tunnel boring machine with a diameter of 57.4 feet, built specifically for the Alaskan Way viaduct replacement project led by the Washington State Department of Transportation in Seattle. The machine was assembled in Osaka, Japan, and launched in July 2013, an ideal moment to showcase advancements in American transportation infrastructure and to confront the growing risk of a major earthquake. At the time of its manufacture, the $80 million machine was the largest earth pressure balanced tunnel boring machine in the world, representing an extraordinary level of technological sophistication. Bertha even featured a unique pre-programmed melody that played for workers inside the machine and for engineers monitoring the drilling operation above ground. Yet Bertha's story did not truly begin in 2013, as the world initially believed. The vision behind this colossal undertaking dates back to 2001. In February of that year, 12 years before, Bertha's launched, the rural community of Nisqually, Washington, became the epicenter of a magnitude 6.8 earthquake, later known as the Ash Wednesday earthquake. The seismic event violently shook the region. In Seattle alone, nearly 400 people were injured, and one person tragically died of a heart attack. While the human toll was severe, the region's infrastructure suffered the greatest damage. Subsequent inspections revealed a disturbing reality. Much of Seattle's existing infrastructure would not withstand another major earthquake. In response, city officials rapidly organized a comprehensive program to restructure public infrastructure addressing nearly every vulnerable system, all except one critical structure, the Alaskan Way viaduct. Although repairing the viaduct posed serious risks, engineers were unanimous in one conclusion: it would not survive another significant seismic event. Replacement was inevitable. After years of debate and planning, authorities decided to demolish the viaduct entirely and reconnect the northern and southern sections of State Route 99 through a $3.1 billion tunnel, rerouted away from the waterfront, the viaduct's original alignment, and the aging Battery Street Tunnel. The new tunnel would pass beneath downtown Seattle at a depth of approximately 200 feet, carefully threading its way below a dense maze of piles, cables, and pipelines, supporting more than 160 buildings above. It was a massive project, and engineers needed a primary tool: Bertha, the largest tunnel boring machine in the world. After being manufactured in Japan, Bertha was disassembled to facilitate transport and shipped to Seattle, where it was reassembled. It was simply too large to cross the ocean fully assembled. The gigantic machine consisted of a cutting head weighing about 2,200 tons, slurry piping, a shield, a control room, and a trailing gear assembly. On July 30, 2013, the assigned engineers began operating Bertha under the watchful eyes and cameras of the international media. The TBM started excavating a concrete plug, with expectations of emerging on the other side of downtown 14 months later. Although it appeared to be a normal excavation process on the surface, Bertha would face dangers beyond rock and clay. Bertha's breakdown. Despite the entire megatunnel route being studied and multiple test borings conducted, the detailed geology of the construction area remained uncertain. The soil in the designated area was complex, with layers of varying composition, so drilling was closely monitored. Since Bertha was also a one-of-a-kind machine, its navigation involved uncertainties. Still, the operating engineers were determined to learn and solve whatever challenges arose during the work. In December, 5 months after excavation began, Bertha suffered a catastrophic failure that nearly ended the entire tunnel program. The massive TBM struck a steel pipe and shut down after excavating about 1,083 feet underground. An inspection engineer had reportedly left the steel pipe behind by mistake while measuring the groundwater table. 3 days after the incident, the situation worsened. Rubber seals around the main bearing failed, allowing debris to enter and damage critical components of the machine, which began to overheat. All on-site attempts to restart it failed, and 2 months later, Bertha remained stuck at a depth of about 118 feet, with no way out. With no solutions from field engineers, Hitachi, the machine's manufacturer, concluded that the only way to repair Bertha was to excavate down to it and partially dismantle it. After months of complex legal proceedings over repair funding, disputes, and sample inspections, the repair was finally completed in December 2015. Just days before Christmas, Bertha began moving again. Engineers breathed a sigh of relief, but the worst was yet to come. 1 year after resuming excavation, Bertha passed through a layer of stiff clay mixed with sand and gravel, at a depth of about 118 to 151 feet beneath the viaduct, causing a sinkhole to open approximately 98 feet behind the machine. Bertha was shut down again for 6 weeks, while engineers filled the cavity. When operations resumed 3 months later, Bertha was ready to proceed. At a depth of around 200 feet, the TBM bored through the city for 11 months without major issues. Then, after a final trajectory correction of about 6 inches in March 2017, Bertha was ready to fulfill its purpose. On April 4th, the massive TBM broke through the concrete plug of the reception shaft built for it, kicking up clouds of dust as the media watched. Although Bertha made history, its ending was bittersweet. After the job, engineers began dismantling each part of the giant machine into smaller sections weighing about 22 tons, so they could be transported by road and reused in the construction of other infrastructure projects. Although Bertha was historic for the United States and the world, it was not the only giant tunnel boring machine ever built. The United States held another major secret it tried to keep out of the spotlight: the mysterious TBM that discovered artifacts. After Bertha, the United States decided to do something even more ambitious in tunnel construction and quickly funded another project, this time in secrecy. The Chesapeake Bay Bridge Tunnel project began in 2017 in Virginia, shortly after Bertha's work concluded. The project, however, faced many obstacles. Initially planned on a 5-year schedule with completion expected in 2022, numerous delays added another 5 years to the timeline, far beyond original expectations. After several delays related to toll revenue, the United States introduced a giant tunnel boring machine named Chessie, which began excavation in February 2023. Chessie had bored only about 755 feet when workers noticed large pieces of steel on the conveyor belt that carries excavated material from the tunnel up to the surface of the bay. After further investigation, engineers discovered that the steel fragments were artifacts, possibly from a ship more than 50 years old. One of the pieces was engraved with the name W.L. Byers & Co., a company based in Sunderland, England, which produced anchors from the 19th century until around the 1950s. No one knows how the anchor was buried or which vessel it belonged to. The British anchor was fairly common, weighing about 4 to 5.5 tons, but it was crushed by Chessie during excavation. Engineers shut down Chessie to investigate the delay. After analysis, they excavated and replaced damaged parts of the machine caused by the anchor. The crushing caused significant damage to Chessie's cutting head. Of the 442 components in the cutting heads, such as discs and scrapers, 389 had to be replaced. For more than 6 months, on-site engineers worked on repairing the damaged parts and advancing the tunnel. For an additional 3 months after replacement, the construction team focused on bringing Chessie's cutting head back to full operation. The cutting head was about 300 feet long. Although the obstruction caused by the anchor added 241 days to the project, Chessie resumed operations, boring about 50 feet per day and reaching approximately 1,600 feet, in total about 25% of the planned 6,400 feet. The giant TBM is expected to complete its work by late 2027. Chessie and Bertha are impressive, but they are not the only tunnel boring machines carving through the underground. There are many types of TBMs, some even more sophisticated. To understand each type, however, it is first necessary to understand how they generally operate. How tunnel excavation works. Tunnel excavation is a mechanical operation designed to open complete underground passages. Although it may seem simple, the process is far more complex than it appears. A tunnel boring machine typically weighs over 6,600 tons and measures about 490 feet in length. Because a TBM cannot make sharp turns due to its size, it carries out excavation through a rotating head, also known as a cutting head, which drills into the ground using a hydraulic or electric motor system. Depending on the characteristics of the tunnel, the cutting head can be manufactured from different materials. The machine generates a thrust force that ensures the rotating head continues advancing during drilling. Behind the TBM is a rail-mounted platform called the support equipment, or backup, where additional working systems are installed, such as transformers and ventilation fans. This assembly also contributes to a continuous and stable excavation process. After each section is excavated, the TBM is stopped and structural rings are installed inside the tunnel to keep it stable as the machine advances. Tunnel boring machines are not the only construction mega machines in existence. They represent only a fraction of the largest construction machines ever produced. The Bailey Z75710, the largest off-highway dump truck in the world, has an estimated value of $7 million. This dump truck exists in different configurations, with versions weighing 99 tons and others 143 tons. It is capable of carrying 496 tons and withstanding up to 551 tons in overload, which earned it a Guinness World Record. It also holds another Guinness record for being the largest vehicle by cubic volume, with 22,800 cubic feet. Its length is about 66 feet, its width reaches 33 feet, and its height exceeds 26 feet. When fully loaded, its total weight reaches 937 tons, equivalent to the weight of two large Airbus A380 passenger aircraft. When it needs to be transported to a work site, it is too large to travel on highways. Instead, the truck is disassembled and transported on 20 railway flat cars, occupying nearly an entire train. It is equipped with two 16-cylinder engines, each producing 2,300 horsepower, for a combined output of 4,600 horsepower. Each engine has about 76 liters of displacement, totaling more than 152 liters, roughly 100 times larger than the engine of an average car. The engine generates nearly 7,400 pound-feet of torque. For comparison, a Toyota Hilux produces about 370 pound-feet, approximately 20 times less. This power drives to generators that produce around 3,500 kilowatts of electricity. This vehicle could supply power to about 1,000 apartments, assuming a small apartment consumes an average of 3.5 kilowatts. The Bellesi 75710 has 4 axles, each driven by its own electric motor, with 1,600 horsepower per motor. For this reason, the Bellesi can be considered an electric vehicle, as it is propelled by 4 electric motors. The generators supply power to all axles, driving the 8 wheels. Each of the 8 tires weighs nearly 6.6 tons, and the cost of a single tire ranges between $50,000 and $90,000. Equivalent to the price of 2 to 4 economy cars. Each tire has a diameter of about 13 feet and is inflated to approximately 100 psi. If a tire of this size were to explode, the impact would be comparable to the detonation of 3 hand grenades. The fuel tank holds 740 gallons, about 55 times more than that of a Hilux. The massive Bellesi truck travels about 62,000 miles per year and can be used for 10 to 12 years. Over its service life, it can exceed 620,000 miles. It has 8 air filters that must be replaced frequently, as it operates in extremely dusty quarries. The Bellesi was first introduced to the world in 2012. Currently, 5 manufacturers, including Bellesi itself, produce this type of large-scale machine. The truck's top speed is 40 miles per hour. Its compact cab features 2 seats, an automatic transmission, 2 brake pedals, an accelerator pedal, and a climate control system. During operation, one of the engines runs at about 800 revolutions per minute. The next Colossal machine is the largest front-end loader in the world, the Laterno L22-350, manufactured in Longview, Texas, by the company Laterno. This giant loader moves minerals such as gold, coal, copper, ore, and other materials into larger trucks. It weighs more than a Boeing 737, stands as tall as a 2-story building, and is capable of lifting the weight of 40 cars above its head. The loader features a rock bucket with a capacity of about 1,340 cubic feet, capable of lifting up to 88 tons. To give a more practical sense, approximately 1,400 cubic feet corresponds to the load of about 5 standard dump trucks commonly seen on highways. Front-end loaders are relatively recent compared to other types of excavators. Although Laterno has a long history in manufacturing loaders, the L2350 was the first model of this size to roll off the assembly line. Near the factory, there is a test field where the machine undergoes various evaluations. The Laterno L2350 was designed because increasingly larger trucks required even more powerful loaders. As trucks grew in size, engineers spent 2 years developing a loader capable of lifting 50% more load than the previous model. The company even partnered with Firestone to create the largest tires in the world. These tires are about 13 feet tall, more than 5 feet wide, and rank among the largest rubber components ever produced. Laterno manufactures many of the L2350's components at its Longview plant, where it also operates its own steel mill. The L2350 structure includes a radiator with a capacity of approximately 150 gallons of coolant. It is equipped with a massive 16-cylinder turbocharged diesel engine with aftercooling, producing about 2,300 horsepower. During operation, fuel consumption reaches approximately 50 gallons per hour. The diesel engine drives a generator, which supplies electricity to 4 electric motors responsible for moving the loader. Massive hydraulic cylinders about 16 inches in diameter raise the giant bucket, capable of collecting enough material to fill an Olympic-sized swimming pool in just a few passes. The Caterpillar 6090 FS is one of the most impressive machines on the planet. Weighing around 1,210 tons, equivalent to stacking more than 1,000 mid-size cars. Its enormous size and weight highlight the exceptional level of engineering and design involved. Powered by a robust 793 horsepower engine, the Caterpillar 6090 can excavate to depths of up to 121 feet and move up to 268 million cubic feet of material per day, equivalent to excavating a soccer field to a depth of more than 100 feet in a single day. This extraordinary capacity is ideal for large-scale projects such as bridge construction, high-rise buildings, and mining. Equipped with advanced technologies such as GPS, 3D modeling, and automated controls, the 6090 excavates with precision and efficiency, speeding up work while reducing fuel consumption and operating costs. Sensors and cameras provide the operator with a complete view of the excavation process, allowing real-time adjustments. These high-tech features make the 6090 indispensable in construction or mining operations. The machine also features an intuitive control system that simplifies operation. The operator's cab is designed to provide maximum visibility and comfort, reducing fatigue and improving control. Maintenance is streamlined with a centralized lubrication system that facilitates greasing of moving parts and multiple access points for quick servicing. Beyond excavation, the versatile Caterpillar 6090 is well suited for mining, construction, and demolition. Its size and power make it ideal for large-scale projects, and it is equipped with multiple safety systems, including emergency shutdown, fire suppression systems, and rollover protection structures. Its advanced technology ensures precise and efficient excavation, reducing fuel consumption and overall costs. Over time, it can generate significant savings for companies. Designed with environmental considerations in mind, the machine includes emission reduction technologies to minimize environmental impact. The centralized lubrication system also reduces oil leaks and spills, contributing to more sustainable operation. The size, power, and advanced technology of the Caterpillar 6090 allow it to perform tasks that are impossible for smaller machines, while maintaining a high level of precision and efficiency. The L1-300 crawler crane, in turn, has a lifting capacity of 3,000 tons and successfully lifted a 3,370-ton test load at its factory in Ehungen, Germany, earning the title of the most powerful conventional crawler crane in the world. Designed to lift its maximum load at a 39-foot radius, the L1-300 is ideal for applications such as power plants, especially nuclear facilities with large pre-assembled modules and refineries, where columns can weigh up to 1,650 tons and reach heights of 328 feet. Each crawler track stands over 11.5 feet tall and weighs more than 220 tons. The hook block alone weighs 122 tons. The crane's maximum system length reaches 807 feet, achieved with a 66-foot main boom and an 85-foot luffing jib. For boom configurations can be combined light, medium heavy, heavy, and super heavy. According to the manufacturer, the LR1-300 is unique in that it can operate without a derrick counterweight, thanks to an internally manufactured slewing ring. When used with a derrick, it features an adjustable suspended counterweight system similar to that of the LR1350, which can be guided within a 66 to 98-foot radius. A trailer-based ballast transport system is also available, combining the standard suspended counterweight assembly with a modular heavy-load trailer. For transport, the maximum weight of each component is 77 tons. Fully equipped with 440 tons of ballast on the superstructure and 1,650 tons of derrick ballast, the L1-300 reaches a total operating weight of 3,860 tons. Most components are under 11.8 feet in height and 13 feet in width. The crawler frames, measuring more than 5 feet high, about 66 feet long, and weighing approximately 230 tons, are transported after removing and dismantling the 90-ton crawler assemblies. The 141-ton main structure is divided into two sections and transported on low-bed trailers. The 14.8-foot diameter slewing ring is transported diagonally to remain within the 13-foot width limit. To facilitate transport, the concrete ballast blocks are designed to match the dimensions of 20-foot shipping containers. Big Muskie was the largest and most impressive walking dragline ever built. Known as Big Muskie, it had truly colossal proportions. It stood nearly as tall as a 22-story building and weighed around 11,000 tons. The Central Ohio Coal Company had a new project underway. Its mine covered more than 172,000 acres of rugged terrain, and the company needed a gigantic machine to remove overburden and extract coal. The factories of the Bucyrus-Siri Company were tasked with designing and building the components of Big Muskie, a machine of extraordinary dimensions. In 1969, after 3 years of work, the Colossus was ready to operate. It took 340 railcars and 260 trucks to transport each component to the mine site, in addition to approximately 200,000 man-hours for assembly. Construction took about 2 years and involved an impressive workforce. The cost was $25 million in 1969, equivalent to approximately $107 million today. Big Muskie's bucket had a capacity of 220 cubic yards, or about 6,000 cubic feet, enough volume to fit 2 full-size Greyhound buses side by side. In 1976, it was reported that this gigantic machine removed about 8,000 cubic yards of overburden per hour for the coal company. Over its service life, it moved twice the amount of earth excavated during the original construction of the Panama Canal. Due to its extreme size, this Colossus required an enormous amount of energy to operate, equivalent to the electrical demand of an entire city. A voltage of 13,800 volts was supplied to the dragline through a trailing cable that powered 18 direct current electric motors rated at 1,000 horsepower each, plus another 10 motors rated at 625 horsepower. This consumption was comparable to the electricity use of about 27,000 homes, making operation extremely expensive, with energy costs reaching tens of thousands of dollars per hour. As a result, the mining company had to negotiate special agreements with Ohio power utilities to support the additional load. Operations ran continuously, 24 hours a day, with nighttime being the most economical period due to lower electricity rates. A remarkable detail is that Big Muskie could move on its own, using its massive hydraulic walking shoes. Its speed was about 0.1 miles per hour, typically traveling less than 1 mile between excavation positions. The machine operated for 22 years, removing more than 600 million cubic yards, or about 460 million cubic meters, of overburden and exposing more than 20 million tons of coal. However, due to rising electricity costs and growing opposition to surface mining in Ohio, the machine was retired in 1991. After remaining idle for 8 years, the state of Ohio enacted the Surface Mining Control and Reclamation Act in 1999, requiring the removal of all equipment from former mines for environmental restoration. Big Muskie was dismantled on site and sold as scrap, yielding about $700,000 in recycled metal. Only its massive bucket survived and is now on display at Miners Memorial Park in Bristol, Ohio. The area where Big Muskie once operated was partially transformed into a wildlife park called the Wilds, opened in 1994, which now hosts various species of African, Asian, and North American wildlife. Now, let's talk about the Komatsu D575A3 Superdozer, the largest and most productive crawler dozer in the world, delivering nearly twice the performance of any other. Komatsu's integrated design provides industry-leading productivity and reliability, along with a wide range of advanced standard features. Hydraulic systems, transmission, chassis, and all major components are designed and manufactured by Komatsu itself. Its engine develops 858 kilowatts, equivalent to about 1,150 horsepower. With turbocharging, the aftercooled engine delivers abundant power, while the giant blade has a capacity of about 3,180 cubic feet. The D575A3 Superdozer reduces operating costs per ton moved thanks to its extremely high productivity. The large blade, with low resistance during pushing, combined with an automatic lock-up torque converter, saves fuel and increases speed by improving power transfer efficiency during long pushes. Komatsu's newly designed PCCS ergonomic control system creates a fully controlled operating environment for the operator. The travel joystick is ergonomically designed to provide a relaxed posture and precise control without causing operator fatigue. Gear shifting is performed easily, using only the thumb. The fully adjustable suspension seat and travel console improve rear visibility during the return phase of the work cycle. The operator can adjust the seat up to 15 degrees to the right. Transmission and steering controls move together with the seat, ensuring maximum comfort. The travel console also features longitudinal and height adjustments, as well as an independently adjustable armrest. Each D575A3 operator can tailor control positions to personal preference. Engine speed is controlled via an electrical signal, simplifying operation and reducing issues caused by mechanical linkage binding. The blade control joystick uses proportional pressure control, a PPC valve, and palm control, similar to the travel joystick. Combined with Komatsu's highly reliable hydraulic system, PPC control enables extremely precise movements. The D575A3 Superdozer uses a new electronic powertrain control system. The controller records operator command movements, switch operations, and machine condition signals from each sensor. Based on this data, the system precisely controls the torque converter, transmission, steering clutches, and brakes, optimizing machine operation. The controller automatically adjusts clutch engagement according to travel conditions such as speed, engine, RPM, and shift patterns. This ensures smooth, shock-free engagement, greater component reliability, extended service life, and increased operator comfort. Large tinted glass windows provide panoramic visibility of the work area. An air filter and pressurized cab prevent dust intrusion. Continuous monitoring of machine conditions helps prevent serious failures and allows the operator to focus fully on control inputs. When a malfunction occurs during operation, the user code and hour meter are displayed alternately. For high-priority codes, a warning light illuminates and an audible alarm sounds to prevent escalation of the issue. Komatsu's efficient engine, combined with the machine's heavy weight, makes the D575A3 a superior crawler dozer in pushing productivity. The engine is designed to exceed standards set by the U.S. Environmental Protection Agency and the California Air Resources Board, featuring direct fuel injection, a turbocharger, and an intercooler to maximize efficiency. The engine is mounted to the main frame with rubber isolators to reduce noise and vibration. For greater efficiency during long pushes, lockup mode allows the system to automatically engage the torque converter clutch. When the torque converter is locked, all engine power is transmitted directly to the transmission, increasing ground speed and achieving efficiency comparable to a direct drive transmission. The system delivers powerful traction, component durability, and operator comfort. Excellent traction is ensured because the track shoes conform closely to ground contours. The X-frame boogie structure, with a resilient and equalized track system, allows independent oscillating movements. Rubber dampers are installed in the X-boogies to reduce vibration and impact. These assemblies provide different absorption characteristics depending on ground conditions. The remote electric unit functions as a conventional rigid chassis when the machine travels on flat terrain, but maximizes suspension effect on uneven ground. Standard equipment includes a preset speed selection function, allowing the operator to choose from 3 forward and reverse travel patterns. When a preset pattern is selected and the joystick is engaged, the machine automatically travels at the corresponding speed. This feature reduces operating time and the need for manual gear shifting during repetitive cycles. The automatic downshift function monitors engine, RPM, selected gear, and travel speed. When a load is applied and speed decreases, the system automatically shifts to the ideal gear, ensuring high fuel efficiency. This results in more comfortable operation and increased productivity. The Bagger 288 is a bucket wheel excavator, or mobile surface mining machine, manufactured by Krupp in Germany for Rheinbraun Energy and Mining Corporation, at a cost of $100 million. When completed in 1978, the Bagger 288 became the largest land vehicle in the world, surpassing NASA's crawler transporter used to carry the Space Shuttle and the Saturn V rocket. It weighs about 49,600 tons, stands 312 feet tall, and measures 707 feet in length. Development, construction, and assembly of the machine took 10 years. This German machine is one of the largest land vehicles ever built, taller than the Statue of Liberty and heavier than the Eiffel Tower. Excavators of this type are capable of removing entire areas, even cities, and are used in open-pit mines around the world. The Bagger 288 can move about 314,000 cubic yards of soil per day with its rotating bucket wheel. It was designed to remove overburden from the Hambach surface coal mine in Germany before extraction began. In a single day, it can excavate the equivalent of a football field to a depth of 100 feet, or remove about 292,000 tons of lignite coal. Within its structure, for conveyor belts collect soil, rock, or coal from the buckets and transport the material at speeds exceeding 11 miles per hour. Each belt is about 10.5 feet wide enough to carry a compact car. The machine moves slowly, at approximately 0.4 miles per hour, supported by about 8,600 square feet of crawler tracks. The excavator is powered by approximately 5,600 feet of electrical cables, each about the diameter of a human arm. Its structure uses about 44 tons of paint and includes 246-foot-tall pillars and more than 7,200 feet of suspension steel cables. The bucket wheel stands about 72 feet high, equivalent to a 7-story building. The 18 buckets weigh approximately 3.9 tons each when empty and can carry about 230 cubic feet of soil, enough to fill a dump truck. For electric motors drive this giant excavator with a combined output of 3,360 kilowatts, equivalent to the power of dozens of passenger cars. When moving over grass or soil, the machine leaves tracks no deeper than a human footprint. The Bagger 288 advances at a speed of about 33 feet per minute and requires at least 3 weeks to complete a 14-mile relocation. The machine has crossed rivers, but doing so required extensive preparation. At least 70 people are needed to clear the path, and the most recent river crossing cost about $10 million, although it does not need to be dismantled during mining operations. Transporting it on its own tracks has proven more economical than disassembling and reassembling it at a new location. Today, it is owned and operated by RWEAG, a major energy company, and forms part of a fleet of similar large-scale machines. No other earth-moving machine is capable of moving mountains like RWE's Bagger 288. Thank you for watching. See you in the next video.